Imagine falling seriously ill, and your doctor needs to look inside your brain, not at your skull, not at a shadow of your brain, your actual brain, its soft tissue, its structure, perhaps even the tiny abnormality causing your symptoms. There is only one problem. Nobody wants to cut open your head just to take a look. Today, doctors have another option. They can place you inside a machine, switch on an incredibly powerful magnetic field, send radio waves through your body, and use signals from the hydrogen atoms inside you to construct remarkably detailed images of what lies beneath your skin. No knife. And unlike an X-ray or CT scan, no ionizing radiation is required to create the image. This is magnetic resonance imaging, MRI. And the strange story behind it begins long before anyone imagined putting a human being inside one. To understand MRI, we first have to travel back to the 1940s. Scientists were investigating something called nuclear magnetic resonance. Thankfully, the basic idea is much easier to understand than the name. Your body contains an enormous amount of water, and water contains hydrogen. At the center of a hydrogen atom is a proton. You can think of that proton, very roughly, as behaving like a microscopic magnet. Normally, all these tiny magnetic effects inside your body aren't neatly arranged, but place them inside a powerful magnetic field, and something remarkable happens. Many of them become aligned relative to that field. Now introduce a carefully chosen pulse of radio frequency energy, and you can disturb that alignment. When the pulse stops, the protons move back toward their previous state. As they do, they produce detectable signals. Different tissues behave differently. Fat, muscle, fluid, brain tissue. Disease can also alter tissue properties. So hidden inside those signals is information. The problem was, scientists could detect the signals, but they couldn't initially tell exactly where inside an object each signal had come from. They could hear the orchestra, but they couldn't tell where each instrument was sitting. Then, Paul Lauterbur had an idea. In the early 1970s, Lauterbur deliberately introduced small variations into the magnetic field. These were called magnetic field gradients, and those gradients changed everything, because now signals coming from different locations could be distinguished from one another. Suddenly, magnetic resonance wasn't merely telling scientists what substances were present, it could help reveal where they were. In 1973, Lauterbur published work demonstrating magnetic resonance imaging using small tubes containing water. The resulting image was crude by modern standards, but conceptually, it was enormous. Magnetic resonance could create a picture. Meanwhile, across the Atlantic at the University of Nottingham in England, physicist Peter Mansfield was pushing the technology further. Mansfield developed mathematical techniques for interpreting the signals efficiently. He also worked on methods that would dramatically accelerate image acquisition. Because there was an obvious problem. A medical scanner isn't very useful if producing an image takes forever. The physics needed speed, and Mansfield helped give it that speed. But there was another scientist pursuing a different piece of the puzzle, and his role would eventually become one of the most debated chapters in the history of MRI. His name was Raymond Damadian. Damadian had been studying how magnetic resonance measurements differed between tissues. He proposed that these differences might potentially be useful for detecting disease, including cancer. And unlike the small experimental imaging systems, Damadian wanted to build something large enough for an entire human being. The machine was called Indomitable, and it looked nothing like the polished hospital scanners we know today. It was an enormous experimental machine built around a superconducting magnet. Its creators used miles of specialized wire. Liquid helium helped cool the system. A homemade antenna coil helped detect signals, and a platform moved the person through the machine. Then came the test. Damadian initially tried entering the machine himself. It didn't work. The team couldn't obtain the signal they needed. So graduate student Larry Minkoff eventually volunteered. On July 3, 1977, after hours inside the experimental scanner, the team succeeded. They produced a crude cross-sectional magnetic resonance scan of Minkoff's chest. Only 106 data points were used to construct it. Compare that primitive image with a modern MRI, and it barely looks related. But a human body had now been scanned using magnetic resonance. The race toward practical medical MRI was accelerating. This is why saying that one person simply invented MRI misses the real story. Damadian made important early contributions involving tissue measurements and built a scanner that produced an early human body scan. Lauterbur developed the use of magnetic field gradients to generate spatial images. Mansfield developed mathematical and rapid imaging techniques that helped transform the concept into practical imaging. And other scientists and engineers would continue improving the technology. One particularly important chapter unfolded in Scotland. At the University of Aberdeen, researchers developed a full-body MRI system known as Mark I. On August 28, 1980, the machine successfully scanned its first patient. MRI was leaving the experimental laboratory and moving toward the hospital. But how does the giant machine in a modern hospital actually see inside you? Imagine that you're the patient. You lie on a table. The table slides into the scanner. Surrounding you is an extremely powerful magnet. The magnetic field influences hydrogen protons throughout your body. The scanner then sends precisely controlled radio frequency pulses. Gradient coils slightly modify the magnetic field depending on position. When the excited protons relax, they produce signals. Coils in the scanner detect those signals. But what the machine receives isn't simply a photograph. It's data. Huge amounts of data. A computer has to determine where those signals originated, how strong they were, and how the tissue responded. Then mathematics transforms that information into an image. Slice by slice by slice. Your brain, your spine, your joints, your organs, structures hidden completely beneath skin and bone, appear on a screen. And because tissues contain different amounts of water and fat and respond differently to magnetic resonance, MRI can produce extraordinary contrast between soft tissues. That is one reason MRI became so valuable for examining areas such as the brain and spinal cord. And there's another remarkable advantage. MRI does not create its images using ionizing radiation. X-rays do, CT scanners do. MRI instead relies primarily on powerful magnetic fields, radio frequency energy, gradients, and computers. But that doesn't mean an MRI scanner should ever be treated casually. That magnetic field can be extraordinarily powerful. Certain metallic objects can become dangerous near an MRI scanner. Some implants and medical devices require careful screening for MRI compatibility, which is why hospital staff ask so many questions before allowing someone into the scanning room. And then there is the noise. If you've ever had an MRI, you probably remember it. Bang, 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 clack, clack, clack. Those sounds are produced as the scanner's gradient system rapidly switches during imaging. Inside that futuristic machine, some very serious physics is taking place. By the 1980s, MRI was becoming a practical clinical technology, and it continued improving. Scans became faster, images became sharper, computers became vastly more powerful. Specialized techniques were developed. Doctors could examine tumors, injuries, the spine, joints, blood vessels, and incredibly detailed structures inside the brain. Eventually, researchers developed functional MRI, or fMRI, which can detect changes associated with blood oxygenation and blood flow. Instead of merely examining what the brain looks like, scientists gained a way to study patterns associated with brain activity. A machine born from experiments in atomic physics had become a window into the living human brain. Then, in 2003, Paul Lauterbur and Peter Mansfield received the Nobel Prize in Physiology or Medicine for discoveries concerning magnetic resonance imaging. Their work had helped transform magnetic resonance from a laboratory phenomenon into one of medicine's most powerful imaging technologies. And perhaps the most astonishing thing about MRI is what the machine is actually doing. Think about it. You enter as a human body, but to the scanner, You are an enormous landscape of atoms. Magnetic fields influence their behavior. Radio waves disturb them. They respond with signals too subtle for you to feel. The machine listens. Mathematics determines where those signals came from, and a computer transforms them into an image of a world that your eyes could never see. Your brain, your spinal cord, your muscles, your organs, all without making a single incision. For thousands of years, the only way to truly see inside the human body was to open it. Then physics gave us another way. We learned to ask the atoms themselves. And listen, when they answered. This is ShowHowGram, 365 inventions, one extraordinary story at a time.